Hello again, advanced AI arcane artists. Are you ready to dive deeper into the arcane arts of Numpy? This is video 10 out of 20 in our beginner series and introduction to AI. Now in the last video, we unlocked the basics of Numpy. This time, we're going to venture into the advanced spells and methods that power neural networks and AI wonders. The first is the arcane art of magical extraction from an array. Now you did this last time with me, where slicing and indexing are like extracting a specific potion or an ingredient from a magical recipe. You'll see how we can create sub-matrices, which might feel like a review, but then I'll show you the concept of indexing, which allows you to return a very specific element. So again, first we're going to import the NumPy library as NP, and now I'm going to create a 2D array. So we'll name it matrix. As you guys remember, you need the 2 brackets for a 2D array. And let's populate it with our favorite sequence from 1 through 9. All right. Now that we've created this, I'm going to actually begin slicing it. So when I'm slicing it, we're going to call it the submatrix. And what I'm doing here is I'm actually going to just do mtx. And like in the similar example, we'll just pull out 0 to 2. And then I'm going to write comma, and then 1 to 3. This will then allow me to print that sub-matrix, or sub-mtx. Next to it, I'm also going to show you how indexing looks. So if I click on element, and then I do mtx, and we'll just look at 1 and 2, we'll print, and then that element. And you know what? Why don't we also print the regular matrix, so you can see how all of these compare. All right, so let's take a quick look at what that matrix does when I perform these types of operations. What you should understand is that there are more advanced mathematical functions as neural networks thrive on math. But first, let's dig into what this means with slicing and indexing. When I called upon 0:2, what ended up happening here is that the first value that returned was actually 2, 3, and then I also called on 1:3, which returned 5 and 6. And so what this is telling me, what it's pulling out, if this makes sense to you, is that it's saying, hey, let's slice out just the submatrix of essentially the last 2 columns. And that's what you're seeing here when you see I only return 2, 3, 5, 6. I'm going to hover my mouse, so you'll see what I returned were only these 2 sections of the full matrix. That's all that we sliced when we designated 0:2 and 1.3. And so again, what this did was it basically told us, let's ignore this outer element of 1, 4, 7, 8, and 9. Finally, with the element of matrix 1, 2, what this did was it basically went into the first row, and then it also went into the second index of the column. And so remember that these index based off 0, 1, 2, so the first row is actually this one, and then 2 is referring to this value, because again, remember that in NumPy, you index beginning at 0. So 4 would have been 0, 5 would have been 1, and 6 would have been 2. So matrix 1, 2 pulls technically the last column, and then 1 refers to this, in other words, the middle row. Because when you index these, this row is referenced as 0, this row is referenced as 1, and this row is referenced as 2. Hopefully that makes a little bit more sense. Remember, the part that makes this a little bit tricky is knowing that indexing always begins at 0. So it does throw off some people. So now I'll quickly surface element-wise and matrix-wise multiplication, followed by conducting an exponential operation. So let's pull this out and let's just show you what it looks like to perform, element-wise multiplication. So we'll use our trusty variables of A and B, again, 2, 4, 6, and then B, 5, 10, 15. Why not? So then the multiple result, or the multiplication result, you can actually just call NP and then multiply AB. And then you can actually print res. So here you'll see that we multiplied each of these with each other. Element-wise, so we got 2 times 5 is 10, 4 times 10 is 40, and 6 times 15 is 90. So that makes sense. Now let's try to perform matrix multiplication. Here, if you do dot res, and then we do np dot ab, you'll do np dot res, and what you get is actually 140. So for those of you who are familiar with linear algebra, you'll recall that getting the dot product actually takes vectorized data and returns a scalar. And in this case, we got a scalar value of 140. Now, let's finally perform an exponential operation. And so I'll call it exp_res, and then you can actually do this with np.exp, and then we'll pass an a. And so what this does, first let me demonstrate. So print exp_res. What this does is actually it takes our values of 2, 4, 6 and it exponentiates it, resulting, of course, in these following values. Okay, so number 3 is like a shapeshifter spell. Let's change gears a little bit. And this is a critical concept in Numpy known as broadcasting. Now, this capability allows arrays of different shapes to successfully interact harmoniously. So I'm going to show you what that looks like now. So I'll show you broadcasting in action. You've got a matrix. And again, we'll do our trusted sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9. Look at my vector. And this will just be a single array. And now here, we'll actually take these and we'll combine both the matrix with the vector. And then we'll print the result. So as you'll see, you'll notice that you were able to actually magically shapeshift that vector to match your matrix. And all we did was actually add the vector to the matrix. That is the beauty of broadcasting. And so let me explain this one more time to make sure we're super clear. Broadcasting in Numpy allows arrays of different shapes to be used in arithmetic operations. It does this by stretching the smaller array across the larger array shape in a way that doesn't actually use extra memory or duplicate data. Essentially, the smaller array is virtually replicated to match the shape of the larger array so that they can be compatible for element-wise operations. So, in the above example, the smaller array, or vector, was virtually replicated to match the shape of the larger array matrix so that they could be added together. Okay, now we're going to change course again and focus on number 4, which is the beauty of a locator charm. It's helpful when you need to find literally where a specific element in your matrix is based on unique conditions. So I'm going to call this Boolean indexing. So I can call it data, and I'm going to bind another matrix here. And in that array, I'll just build it incrementing by tens, and it'll just be a singular vector. And then what we're going to do is we'll call it filtered, and I'll call this filtered data. But what you then do is you actually establish the conditions. So you only want data that will be greater than 35. Does that make sense? And so I actually pass that as the input to data. And then if you print filtered, let's check out what we get. And there you have it. You actually only return the last two values of 40 and 50 because they satisfy the requirement of being greater than 35. Notice that with this charm, you've been able to now filter out numbers greater than 35. Now, number 5 is probably the most interesting. This is how we simulate tweaking neural network weights as an application of some basic concepts that you saw earlier. So first I'm going to initialize new weights. And let's scroll down so you can see everything. Weights equals np random, and I'll do random 5. Now, just so you have awareness, we're going to add some text as well. So original weights. And then I'll call those values here weights. Just so, let's see, and we got a little error here. Interesting. Looks like the random field is not working for us. How weird is that? We might not need that anymore. It's because I typed it out wrong. It's a sub-function of random. My bad, team. So now if you click out on weights equals np.random.randn, and then you run it as 5, you'll see that we then stored it as a vector of 5 values, 1, 2, 3, 4, 5. These were our original weights. And now what I'm going to do is actually bring in adjusted weights for demonstration. So we'll make up a sort of hypothetical learning rate, 0.01. We'll generate our gradient here. So I'll sort of hard code the gradient. First value being 0.5, the second value changing by minus 0.1, the third value changing by 0.8, fourth value changing by minus 0.05, and the fourth increasing by 0.9. And what you do is you actually take the weights, and this is literally what's happening. You subtract or you update them with this minus equals, and then I take the learning rate times that gradient. And then if you print that adjusted weight, then you click on weights again, you can check out what this actually looks like. And so you'll see that these values indeed were updated or changed. So just like that, you essentially took some random weights and caused the network to learn by subtracting the product of the learning rate and the gradient from the original weights. In that way, your neural network just learned and evolved. Finally, for those of you interested in running AI in sentences and language, you might also be interested in understanding how we can vectorize a sentence as our 6th hint in this video. So we can do this by vectorizing a sentence in the following example. And again, when I say I'm vectorizing a sentence, that actually means that I'm converting its words into numerical representations, often using pre-trained embeddings or simple one-hot encoding. So first you got a sample sentence. Let's say sentence equals, I am learning AI. And then here you want to convert to a one-hot encoded vector. So what we do is we take vocab, and then you can actually call the function sorted. We use a set, which is a type of dictionary-like structure. I take my sentence, and then I split it. So the split allows me to actually split it based off each of the gaps in each of the token words. And then in one-hot vectors, I then initialize, like you saw in earlier examples, my zeros matrix, and I want it to be the length of the sentence, but then I also split it again. And so you'll see that you also want the one-hot vector to have the dimensionality of both the length of the vocab for its columns and then the length of its sentences for its rows. And then what happens here is I want to iterate. So for every I and a word in our now enumerated sentence, you basically want to iterate and populate those new values. So one-hot vectors, and I just realized I typoed, so let's fix that. One-hot vectors I vocab index word, and I want to set that equal to 1. And now this should actually print those 1 hot vectors. And you'll see that we actually changed it into a representation where each of these captures one of these words. I am learning AI. So in this example, we've used 1 hot encoding to vectorize the sentence. Each word in the sentence is represented by a vector, where only one element is hot or set to 1, while the rest are cold or set to 0. The position of the hot element corresponds to the word's position in our vocabulary. Now, 1 hot encoding is a method of representing categorical data as binary vectors, where each category is mapped to a unique vector with all zeros except for a single 1 at the category's index. Now, we use it because many machine learning algorithms and neural networks require numerical input features, and 1 hot encoding provides a way to convert categorical data into a format that can be fed into these models without reintroducing ordinal relationships that aren't present in the original data. Behind the scenes, for each unique category or label in the dataset, a new binary column is created, and each instance is marked with a 1 or 0, depending on whether it possesses that label or not. All right, AI arcane alchemists, you've journeyed deeper into the NumPy labyrinth, mastering smells and incantations that are the backbone of applied AI engineering. As you venture forth, remember, the true magic lies in experimentation. This is video 10 out of 20 in our beginner series and introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. Now roll up those sleeves, dive into the code, and let your AI genes take flight. Until next time, may your algorithms be ever insightful and your code ever bug-free.